Hello everyone. So today we are going to learn about discrete random variables. Starting from this point onward, we are going to learn about random variable, basically discrete and continuous. Then for each type, we will learn about probability distributions. Then we learn about properties of those distributions. So we begin with discrete random variable. So first, what is a random variable? A random variable is actually not a variable. It is a function. So when you have sample space from probability experiment, a random variable is a function um, from sample space to, we can say, to real numbers. Okay. Now, if image of this function, okay, so if I have the image of the function, if it is finite or if it is countable, then we call it as a discrete random variable. So basically what I'm saying is a random variable is actually function from sample space to real numbers. Discrete random variable, we can be more specific. Those function from sample space to integers or natural numbers. In here, I wrote the natural numbers, or you can use integers or subset of that. Okay. That means basically the image of this function is countable. For example, let's say you're going to toss a coin. Okay, so then the sample space is going to be what? You have head and tail. Okay. So this side, your sample space is head, tail, and then you have this function random variable, which is going to assign some values. So let's say you assign 0 to h, head, and then 1 to tail. So basically I'm saying this function going to assign 0 to head and 1 to tail. Okay. So this is random variable. And since the image of the function is countable, or in this case finite, this is discrete random variable. Okay, so this is, if you look at the image of x, what is the image of x, which is 0 and 1, we have it, we can call it as a discrete random variable. Now it's a function, so you remember the properties of function. So you can't assign same element to two values. Okay, for example, I cannot say, let me use a different color. I cannot say something like this. Okay. So this is not a function actually, because then you would have something like this, which is not a function. Okay. But you are allowed to use the, you can assign both to the same value. Like you can say tail value also going to be 0. That is allowed. Okay. So in this case, both are 0. This is allowed. Okay. So this is a random variable and it is a discrete random variable. So now we are going to see some properties. First, we want to talk about probability distribution. So you have a sample space, and then you have function from there to real numbers. Okay, the image of this one can be countable. Okay, so this is image of x, and our current discussion is going to be finite or countable. So this is actually discrete random variable. Okay, later when we go to the continuous random variable, it's going to be uncountable. So in here, now we want to know how this random variable distributed. Basically, for each value of random variable, how the probability are assigned. So let's say x can take value x1, x2, all the way up to xn. Then our question is, okay, let's say random variable take xi. What is the probability for that? Okay. So this is called as probability distribution. This is just one single value, but once you get over all the possible values random variable can take, then you get the probability distribution. Okay. So if I draw a table, it would be look like this. So x can take x1, x2, all the way up to xn, and then I have the probability for that. Okay. So here I have probability x equal x1. For example, in the early example, if you use sample space is head tail, and then you assign this to using random variables to be 0 and 1, then someone can ask, okay, what's the probability for random variable taking value 0? Okay. Let me write it this way. So here I have random variable x, and then this is x equal 0 and x equal 1. This function value, okay, this is actually what? This is x h. Okay. Basically that, okay. So random variable taking 0. So what's the probability for that? Random variable x taking value. Oh, by the way, we use capital letters to denote random variable, and then simple letters, lowercase letter denote the value. Okay, so this is random variable, and this is the value it can take. So now it can be half and half, 0.5, 0.5, or it can be something else. It may be 0.6, and this is 0.4, so forth. So this table we call as probability distribution. Now there are some properties. First one is when you add up across all possibilities, it should be sum should be 1. Okay. So total probability is 1. Now for any given value, I mean the given possibility, random variable taking that value, the probability for that is should be between 0 and 1. It cannot be more than 1, then because probability should be between 0 and 1. So this is called as probability distribution. Sometimes you will see the word probability mass function. Later, when we go to continuous fund, this would replace by a probability density function or PDA. But right now, since we are in discrete, we use probability mass. It look like mass at each point. Okay? For example, if I draw this side I draw random variable x, and this side I draw the probability, and then I can have something like x taking value x1, x2, xn. The probability can be something like, let's say, 0.4. This can be something like 0.2. This may be something like 0.01. So it's look like mass. Okay. So that's why it's called the probability mass function. It's the discrete values. So here you can see a few examples of discrete probability distribution. Binomial, negative binomial, Poisson, geometric, hypergeometric. We are going to go through this distribution later in next module. This time it's just introduction. Just to know that there are specific random variables we are interested, and we are going to learn about specific properties for this distribution. So here you can see that the probability distribution is given using a formula. But this is not possible for each and every discrete random variable. Sometimes you encounter discrete random variables where you cannot give a mathematical formula. Okay? Maybe at that time, maybe you just need the table. Okay? But for these ones, we have a nice mathematical formulation of probability distribution functions. With any random variable, regardless whether it's continuous or discrete, you have to discuss about cumulative distribution function or CDF. Okay. So what is CDF? The definition is this. Basically probability, random variable taking less than or equal to a given value. So this is a random variable, and this is some value. For example, I can ask, okay, what's the probability random variable taking a value less than or equal to, let's say, 10. Okay. So this is CDF. Okay. So you can see X can change. This is the variable. So if I try to graph this side I have X random variable, and then this side I have f of X. Okay. So the first thing is f of X is need to be non-negative. Okay. Of course, because since it's probability, it cannot be more than less than 0. So this is okay. That's true. Then fx is non-decreasing, because when you increase x, you can see that the probability is adding up. For example, let's say probability x less than or equal to this value should be less than probability x less than or equal to 3. Okay, assuming design some ordered way. Okay, so f of x is non-decreasing function, and the limit of x when x goes to infinity, f of x is going to be 1. For example, let's say I use that experiment again, sample space, when you roll the when it was a coin, then the probability of s I can assign random variable. Let me first assign random variable. So this is going to be 0, 1. Then I can calculate the probability x equals 0. Let's assign 0.5, and the probability x equal 1, 0.5. So I can put 0 and 1 here. So you can see that before 0, the value is 0. For example, if I calculate probability x less than 0, it's 0. Then the probability x less than, let's say something like here, 0.7. Of course, you have x equals 0, which is going to be 0.5. So it's going to be up to that, like this. Then from x equal 1, you have another event, x equal 1 probability, we have to add up. So you will get 1. Okay. So this is CDF function. You can see that it's non-decreasing, and it satisfies all these properties given in here. Okay. So here you can see example. It says x is a discrete random variable with probability mass function given by this. So let me put it into a table. So x can take what? X can take 1, 2, 3, or 4. Okay. Since you can see the image of x is random, I mean the image of x is finite, this is a discrete random variable. Then you have probability x taking those values. Okay. So x equal 1 is 0.4, x equal 2.2, x equal 3.3, and 0.1. Now, just quick check. If you add all these probabilities, you can see it's going to be 1. Okay? If you add that, it's going to be 1. And then you can see that each probability in between 0 and 1. So it's a probability distribution. So the first one asks f less than 3. So what is f less f3? What is that? Probability x and a variable less than or equal to 3. So since it's discrete, you can see x can take only what? 1, 2, or 3. So I can break this to what? I can break this as x equal 1 plus probability x equal 2 plus probability x equal 3. Okay. Less than or equal to 3, x can take only of those 3 values. Now if I add those values, it's going to be what? 0.4 plus 0.2 plus 0.3, which is 0.9. So f3 is 0.9. Now graph the CDF for this random variable. So I can graph it. So here I have x, here I have f of x, and we have a few values, random variable x 1, 2, 3, and 4. So what? Let's calculate what happens if x is less than 1. Let's just pick like 0.5. What is f0.5? That's probability x less than or equal 0.5. Okay. you can see that it's going to be 0. Okay. But when x come to exactly 1, if I calculate f1, that's probability x less than or equal 1, which is 0.4. Because less than or equal, you have equal sign. Okay. So this one become 0.4. Okay. Now let's calculate f, let's say 1.5. What is that? Probability x less than or equal 1.5. So somewhere here. Now x can take only 1. So this is same as saying probability x equal 1, which is 0.4. So still 0.4 all the way until you come to 2. Now when you come to 2, what's the probability x less than or equal to? X can take 2 values now, 1 or 2. So this is going to be probability x equal 1 plus probability x equal 2. So it's cumulative, remember? That's why the word cumulative distribution function. So this one is going to be 0.4 plus 0.2, which is going to be 0.6. So somewhere here, 0.6. So you can continue like this, and you would get a distribution look like this. 2.9, and then here it would jump to 1. So that is the CDF. The PMF, probability mass function. So this is CDF. In order to graph the mass function, you can again draw this side random variable, this side is just PMF. So I can say probability x equal x. So I have 1. X equal 1 is 0.4. X equal to 0.2. Remember, it's just for single values. Okay, we are not adding. It's not a cumulative distribution function. For 3, it's 0.3 somewhere here. And then 4 is 0.1. So it will be look like that. So here you can see example. You have two 6-sided fair dice with number 1 to 6. So your sample space is going to be 1. And you would roll them at the same time. Let x be the sum of 2 dice. Okay, so random variable is sum of 2 dice. Okay, so your sample space is actually what? Let me draw the sample space. This is the first die, the second, and then you have 1, 2, 3, 4, 6. Actually, what you have here is just like a dot, no? 2, 1, 1. Both have the dot, dot. Then here you have the first one is 1 dot, the second one is 2 dot. But then you are assigning that to the sum. Okay. So basically, you are assigning sample space to the sum. Okay. So so you can say x plus 1 is 1, second one is 1, assigned to what? 2. The first one is 1, second one is 2, assigned to 3. First one is 2, second one is 1, assigned to 3. Okay, so forth. So this is the function. Okay, basically you are assigning. So let's say a, b. Those are the values from first die and second die, and then you assign it to a plus b. That's a random variable. So you have to construct probability distribution table of x and find f4. So you can write probability x equal x and then x. Okay. So what are x can take? X can be 2, 3, 4, all the way up to what? The maximum should be what? 6, 6 now. It would be assigned to 6 plus 6, which is 12. Okay. Then you can calculate the probability. How many ways you can have 2? The only way 1, 1. No? So there are 36 possibilities. You can see that 6 by 6 is 36. Then only one possibility. Okay. Then how many ways you can get 3? You have actually 2 possibilities. First one 1, second one 2, or first one 2, second one 1. So it's 2 out of 36. So you can create this kind of table, and the 12 you have only one possibility. So this table is called as probability distribution function. Now you have to calculate the F4. What is F4? F4 is the sum is less than or equal to 4. So this would be what? This would be probability x equal to, because 3 plus probability x equal to 4. So how many ways you can get 4? Let's do that. You can have 1, 3, 3, 1, 2, 2. Okay. So we have 3. So then then this F4 is going to be what? It's going to be 1 over 36 plus 2 over 36 plus 3 over 36. It is going to be 6 over 36. Or 1 over 6. Another very useful function, and you're going to learn about this a lot in actuarial science, that's survival function, which is basically complement. Okay. So survival function is defined as probability x, whenever x taking more than x. Okay. Remember the distribution function? That's probability x less than or equal x. So if you add these two, it should give you 1. Okay. So this is called a survival function. You can remember the properties of this distribution function. One was f of x need to be less than or equal to 0. The second one is when x goes to infinity. This one should be 1. Third one is f of x is not decreasing. So here you can replace f of x by 1 minus sx because remember survival function, distribution function plus survival function is equal to 1. By doing that, then you can get the properties of survival function. See whether you can do it. If not, send me an email and we can discuss. Okay, that's all for this section, and then we go to the measures of central tendency in next lecture.